Good evening, everyone. It's a great privilege to introduce today's speaker, Dr. Suresh Sundaram, an accomplished faculty member and researcher at the Georgia Institute of Technology, European campus. With over 15 years of experience in semiconductor optoelectronics and microelectronics, Dr. Sundaram has made a pioneering contributions to the development of 3 nitrates and boron-based material for next generation optoelectronic and photonic devices. Leading a research group equipped with state-of-art MOCVD system, he has advanced technologies like wafer-scale 2D boron nitrate, GaN-based gas sensors, and innovative solar cell structure. His work has widely published with over 80 journals and numerous conference presentations, including collaborations that have drawn global attention. Dr. Sundaram is also a dedicated mentor, guiding multiple doctoral students and postdoctoral researchers in achieving breakthrough in material growth and device fabrication. His contributions have not only expanded the UV photonics and energy efficient devices, but have also inspired young scientists worldwide. Please join me in welcoming Dr. Suresh Sundaram, a visionary scientist in his field. Welcome you, sir. Over to you.
Yes, one more thing, Dr. Suresh from the Crystal Growth Center, Anna University. We are working all together during PhDs. That is on behalf of Crystal Growth Center also. I welcome to the Dr. Suresh from deliver his speech. That is.
Yeah.
Thank you very much.
Thank you. Thank you. Thank you, Dr. Thangavel and Dr. Divakar. So let me start something like this. So I'm really honored to be here to speak among you in the faculty development program. So I thank Dr. Thangavel or Professor Thangavel for the opportunity. You remember me as a colleague in Crystal Growth Center, which I cherish all over my lifetime. Thank you for inviting me for this faculty development program. Thank you again. So let me start by thanking the organizers. So I thank everyone, the organizing team, and the faculties that are available among us now, and also the students and other friends who are really interested in semiconductor processing. Welcome to my talk. So let me start with a small introduction. So they have already introduced my profession, but I am from Anna University. My alma mater is Anna University, Crystal Growth Center. So it has been 15 years, but it looks like it happened just yesterday, and I came here just yesterday.
Yes, like that. More than 15 years.
It's more than 15 years.
Yes.
I graduated from Anna University in 2010, and now I am here from 2010 for more than 15 years. So, okay, that was a good memories. I have all good memories about that. Okay, so let's go into the topic. So today I'm going to present photolithography in semiconductor processing. So I have expanded the title a little bit. So I have added for next generation flexible optoelectronic devices. So flexible optoelectronics is what we are really interested in. So optoelectronic devices is already there in the market. So wherever you go, you will see optoelectronics devices and electronic microelectronic devices. So if you are holding a phone via which you may be watching me or this lecture, it already has microelectronic devices in them. So there is a lot of semiconductor devices in them. So the CPU is made up of semiconductor. As you all know, it is made up of silicon. So there is billions of transistors. I'm going to talk about it. And we are going to talk about a very important or a fundamental process in semiconductor processing. So we are going to talk about photolithography, which is a fundamental step. And then I'm just going to tune you or introduce my field of expertise, which is optoelectronic devices. I'm going to show you how we are using photolithography to realize flexible transferable optoelectronic devices or microelectronic devices or optoelectronic devices. So again, so I'm Dr. Suresh Sundaram. I'm from Georgia Tech Europe, which is an offshore campus of Georgia Institute of Technology. I'm a faculty here. So I will start with Moore's law. So most of you might be knowing what is Moore's law. So it states that, or it's just an observation by Gordon Moore. So he stated that, or he said that the number of transistors on an integrated circuit will double or approximately every 2 years with a minimal rise in cost. So this is a silicon roadmap, or this is the roadmap which was there from 1965, something like that. So every 2 years is an approximate time. So now if you see, it is doubling every 3.5 years. Okay, so but just to tell you a very important thing, how photolithography is affecting this Moore's law. So you can see the technology node evolution. So we were using 365 nanometer UV lights for photolithography. So during that time, during 1990s, the node size was around 250 nanometer. So step by step, we were transitioning towards nanometer size, feature size. The node size has decreased also. All these transition was enabled by the wavelength we are using in the photolithography process. So here you can see that the feature size is approximately 250 nanometer when we were using 365 nanometer, or close to 350 nanometer, 365 nanometer light, and then it came down by 250, or when we are using 193 nanometer, it came down to 22 nanometer. 22 nanometer, 17, 14 nanometer were all possible by optimizing the wavelength we are using. And then when we switched from UV wavelength to extreme UV, we got 7 nanometer, 7 nanometer feature size. And then when we transitioned to extreme UV wavelength and optimize the process further, now in 2024, we are in 3 nanometer node size. So when you are talking about node size, now we are at 3 nanometer, and we are trying to optimize 2 nanometer process. So this is an extreme UV lithography system. So the Apple phone that you might be having in your hands, it has a M4 chip, which has 28 billion transistors of 3 nanometer technology. It was fabricated using this extreme UV lithography system. So you can see that here you have a UV source, which is emitted by a plasma source. So you have to irradiate a CO2 laser on top of a tin foil or tin melt, and then you have to get the source, and then it goes into the wafer stage, passing through different chambers. So the wafer, this is a ASML system, EUV system, or extreme UV lithography system. So this is very special. There is a lot of politics involved in this system. It cannot be exported.
Kindly mute.
Okay, so sorry for that. Okay, so this system is very special, and there is a lot of politics running around the world for this system, and it cannot be exported for some reasons to advanced manufacturers also. They are keeping it for themselves, or the ASML is keeping it for themselves. Only few manufacturers are having access to this system. So as we are speaking about Moore's law, so in 2021, we had this 3 nanometer technology, and we had 16 billion transistors. As I said, the number of transistors in the chip doubles every 3.5 years. So we are 3 years away from 2021. So this 3 nanometer technology now houses 28 billion transistors, almost double or close to double the number of transistors. So this is just to show you how important the photolithography process is. So the system is proprietary of ASML, and it holds the control over all the manufacturers. So let's talk about Georgia Tech Europe. Georgia Tech Europe is a very unique platform. So I am from Georgia Tech Europe. You can see in the photograph, we are a little bit different from Georgia Institute of Technology, but we are coming under Georgia Institute of Technology, but we are based in Europe. So for research and fundings, we are based on Europe. So we rely on European fundings for research. But education comes from Georgia Tech, and we have started education in 1990, and our research from 2006. I am from 2010. I am here, and innovation was started with Institute Lafayette from 2012. Cannot minimize it. It's okay. So I am from this unique platform. So I will start my lecture by giving you something we all know. So semiconductors, we know semiconductors, silicon is a semiconductor, but you are seeing here a microprocessor chip that we use in a CPU, which undergoes like more than 200 steps of processing to go into this TRL 10 state, or technology readiness level 10 state. So what we are doing in our lab is 0 to 3 or 1 to 3 in technology readiness level. If we have prototype, it is close to 5. And if you are transferring this technology into mass manufacturing, you are close to 7. After packaging and devices, you are, when you have a product in your pocket, then the technology readiness level is 10. So the fundamental processing, I said there are more than 200 steps before packaging and things, packaging and passivation things. So, but it can be all classified into 3 major processes. So we need a wafer scale or wafers for enabling semiconductor processing. We need epitaxy, and then we need front-end processing. So my lecture today will be focusing mostly on epitaxy and front-end processing. I believe the previous speakers has talked about the crystal growth techniques which are available to make substrates. And then I will talk about mostly about advanced epitaxy, where we are going to realize 3-nitride systems or 3-nitride heterostructures. And then I will talk about front-end processing, mainly about lithography and other processes related to front-end processing. And then I will finish my lecture. So silicon, as we know, it has a lot of advantages. So it is low cost, high quality, large area substrates are available up to 12-inch. So it has a mature device processing that reliably works. So that's why we are using them, not only because it gives reliability, it's not a high performing material, but we are using it for these advantages. Difficulties with this material is that it cannot emit light. It has indirect band gap, so it cannot emit light. So transistor made with this silicon nitride is also limited. We can go up to few megahertz or few hundreds of megahertz, but not in gigahertz. The bandwidth is limited and it requires more power. So because it consumes more power, it heats up more. So that's why you are feeling a bearable warmth on your laptop, because you need a fan for your laptop, which draws the heat from the CPU and releases into the sink. Sink is the atmosphere here. So general solutions for these kind of difficulties is to change the material. So because we have direct and indirect band gap material, and silicon is indirect band gap, we need a direct band gap material for enabling these light emissions, not only light emissions, to enable high frequency bandwidth for operations. So general solution is to switch materials. So that's why we are more focused on 3-nitrides, which we see as already it is commercially available. All these traffic lights you are seeing, they are based on 3-nitrides. The green and blue LEDs you might be having, they're all based on 3-nitrides. The lasers are all based on 3-nitrides. Red is from gallium arsenide, but we are trying to commercialize red-based technologies through or monolithic integration of 3-nitrides with blue, red, and green, all with 3-nitrides. So I'm going to talk about that. So mainly we focus on optoelectronics and microelectronics. So the list of things we do in our lab. So we are a 3-nitrides lab. We do epitaxy. Homoepitaxy is not possible because for 3 nitrides there is no stable substrate or low cost substrate that is available for epitaxy, homoepitaxy. So we generally talk, if we mean epitaxy in 3 nitrides, it's always heteroepitaxy, and we grow a lot of LEDs, HEMS for transistors and other applications. So we do nano-selective area growth. So for these, we use nano or electron beam lithography system, and then we do a lot of van der Waals epitaxy where we combine heteroepitaxy with a 2D material. So here we have van der Waals epitaxy, quasi van der Waals epitaxy, remote epitaxy. So these are all different kinds of epitaxy that is enabled by 2D materials. So if you want more understanding on this, you can refer to our latest articles. Apart from these epitaxies, we do selective van der Waals epitaxy also, where we will be using a lot of photolithography processes. So I'm going to introduce you to photolithography and all the processes that we do. And then I'm going to take a particular example where we do selective van der Waals epitaxy, and then I'm going to show you how we are realizing devices based on these growth processes. So this graph shows that this graph is a one-stop shop for all the epitaxis we are doing here. So you can see that the region in yellow is where homoepitaxy and heteroepitaxy happens. So this graph is between the binding energy, log of binding energy to the strain. So when we are combining, or when we have covalent and ionic bonding, we have less room for errors, and we cannot move further. We cannot accommodate more strain. So if you are using if you are crossing certain limit, you are above the pseudomorphic formation or pseudomorphic strain layer formation, and then you will relax, forming polycrystals and amorphization. Most probably you will be ending up with single crystalline, but there is a good chance that you will end up in a relaxed or poly or amorphous states. But we know how to grow single crystalline materials on single crystallines. That's what epitaxy is all about. So when we are incorporating van der Waals materials, that is 2D material, we can accommodate more strain. So when we are accommodating more strain, we can grow different kinds of material without any issues. That means we can form heterostructures, or heteromaterials can be combined into one, with exotic properties can be combined into one, and you can have extraordinary physical properties without any physical limits. Okay, that is possible theoretically if you are combining 2D materials with other heterostructures or other devices. That's what we are trying to do here in our lab. So epitaxy, so I believe already a lot of speakers have talked about it. So there is homoepitaxy and heteroepitaxy. So in MOCVD, we generally pass the vapors of the ingredients or precursors over a heated substrate. The heated substrate can be close to 1300 to 1600 degrees C for high temperature materials. So the gas flow, the gas gets, or the precursor gets pulverized on the above the boundary layer, and then diffuses on the boundary layer. There is a lot of mechanisms. For example, surface diffusion, absorption and desorption happens. Once we have stable nucleation, it grows to form a stable layer. So generally, gallium nitride or 3 nitride is grown heteroepitaxially on sapphire substrates due to expensive bulk. Bulks are normally available, but it is very expensive because the process to get bulk crystals are very expensive. And we cannot have a very large sapphire or large substrates. We can have 2-inch max. That's the availability nowadays. So because we are growing it heteroepitaxially, we will be generating a lot of point defects, misfit dislocations, antiphase boundaries, and inversion domain boundaries are there inherently. So this leads to high device leakage currents, short minority lifetimes. So this reduces the thermal conductivity, and then it acts also as a impurity diffusion pathways. So the leakage current of the device will be higher. So this leads to stochastic failures of devices. So the lifetime of your devices, or even though we have reliable performing materials, it leads to stochastic failures. We want to reduce the dislocation density, but we have almost 100,000 hours of working devices. Even the dislocation density is high in these kind of materials. We have reliable performance, but we want to eliminate these dislocations. So the facilities available for the MOCVD growth, we have two MOCVD system, and we have third one. I'm going to show you pictures of that also. So one is a T-shape MOCVD system. It is a custom-made, homemade system, which was designed by Professor Abdullah Usadan in 1990s. So we are still using this system for growth of all three nitrides, including boron nitride. So this reactor is a little bit special. It has a T-shaped reactor. So we load it from the bottom, so you can see the glow of the susceptor, which holds the metal carrier on top of it, and then we'll put the substrates on top of it and then heat up with the RF heater. So the gas flow is horizontal here, so we call it as a horizontal T-shaped MOCVD reactor. So we can deposit all three nitrides using this system. The maximum temperature we can go is around 1050 degrees C. We have another system which is a commercially available AICTE closed couple shower head system. It can hold 3 2-inch wafers, and also it can go a little bit higher in range of temperatures. It can reach 1300 degrees C. Right now we are upgrading this system to 1400 degrees C temperature capabilities. So all three nitrides, including boron nitride, aluminum nitride, indium nitride, and gallium nitride, can be grown. We have already grown the binary, ternary, and also quaternary alloys of these materials using this system. So we have a third MOCVD system which has a larger capacity at Institute Lafayette. Institute Lafayette is our partner institute, which is inside Georgia Tech Europe campus. So there we can, if we have an interesting project, we propose it to them, and if they are interesting, they will give us a time slot for the machine, and we can go and access the machine without any issues there. And then we do our project and then come out without any problems. So it's an open platform. Anyone can use it. Depending on their proposals, they will be selected, and then they will be funded also. There is also funding opportunity where you can come here, and then you can do your work and then leave without any issues. So the system is similar. Only different between the system we have for R&D and in a semi-industrial platform like Institute Lafayette is that it's a semi-industrial platform, so the capacity is a little bit bigger. So it can hold 6 2-inch wafer or 1 6-inch wafer. So recently we have demonstrated a growth of boron nitride and its 3 nitride retrostructures on top of it on a 6-inch scale using this system. So basically what we do is we do gallium nitride based blue LED. I'm taking these as example, but we do a lot of other things also. So we do HEMS, we do sensors, we do detectors, DPVC detectors, photo detectors, and all sorts of 3 nitride based devices. But I'm taking here blue LED as an example. Throughout my slides or throughout this lecture, I'm going to talk about blue LEDs only. So this is the structure, typical structure of a blue LED. So we start with a low temperature gallium nitride buffer on top of sapphire. So this acts as a wetting layer, and then we do a 3 micron high temperature gallium nitride layer. So the growth temperature is close to 1080 degrees C. And then we grow MQWs, where we will be incorporating 3 nanometer thick indium gallium nitride multi-quantum wells, which are the light emitters. And then we'll cover it up with a p-type layer. So normally the holes are injected from the p-type layer, and electrons are injected from the high temperature GaN layer. So when we probe it, we'll normally have a light emission. So for blue LEDs, we'll have blue light coming out of it without any problem. So you can see that this is just a...
Sorry for the interruption, Dr. Suresh. I am Saravanan from Chennai. Your voice is very low. Could you please increase your volume? Maybe I don't. Yeah. We are not hearing clearly.
Okay, so I'll be a little bit louder. I'll try to be
Yeah,
a
yeah,
little
yeah.
bit louder.
Yes,
Okay,
please.
thank you.
Okay, thank you,
Yeah,
thank you.
thank you. So yeah, so these are blue LED structures. It emits blue light around 460 nanometer, but the photolithography starts, or photolithography or front-end processing starts after this wafer growth. So we epitaxially realize these heterostructures and then transfer it for full qualification or full front-end processing. So this is a finalized device. To do this, we have number of steps. So this is the device where we can see blue light coming out of it using a probe station and everything. So normal device size is 300 micron into 300 micron. We can go lower also. So to realize this device, we need to create a mesa and reach the n-type layer so that we can inject electrons into the multiple quantum wells. And then we had to put metal contacts so that we can probe them using probe stations or metal probes without any issues. So this blue light emission that I'm showing here is not a standard way, but after front-end processing with probes, if you are getting blue light, that's a standard way of showing a blue light emission. So this is just for a verification. We do that in our lab every time, but once we grow them, we transfer it to process, and then we do a lot of lithography and other steps to realize a fully fabricated device structures. So dicing and packaging comes later, which we are not going to deal because it is out of scope of today's lecture. So front-end processing or lithography is a fundamental step in microfabrication. So from design to physical patterning. So we go from a wafer which is grown just out of epitaxial chamber or MOCVD chamber. We'll take it to a clean room. We'll clean it. We'll transfer our patterns on top of it and then put metal contacts to finish the device. So these are enabling step for local dry etching or metal deposition. So the lithography step is based on electromagnetic interactions and modification of photoresist via photons or electrons, followed by development. So it is normally done in a very clean environment, in a clean room under a yellow light. So why we need yellow light, I will come to that later. So for this, we use the facilities of Institute Lafayette, which is a high-tech clean room. So here we have control of fabrication technology. So often in atomic precision, we do everything. So it has over tens of fabrication steps to achieve a wafer or LED wafer to finish it to a fabricated wafer. So to achieve these, achieve the final fabricated semiconductor device or a blue LED. So we have over 500 meters square clean room. So it holds both two classes, ISO 5 and ISO 7 class clean room. So lithography, we have optical lithography system. So apart from the MOCVD facility, we have in-house optical lithography system. So it is housed in a ISO 5 clean room. We have a spin coater with EBR, hot plates with pin lift and vacuum contact. So there is developer and spin processor. We use high-end H lines, mask aligner. We can go up to 8-inch tooling. There is no problem with that. So we can also use UV cured nano imprinting technologies for realizing our patterns on these epitaxial structures. So typical resists are S1813. So we don't know the chemistry of these. So these are negative tone resists, but we are using it from the developers. We use typical developers like TMAH and other chemicals. Acetone is also a good developer. So HMDS primer is also used. So UV photolithography, so alignment and exposure tool, which is very important. It's a mechatronic equipment, so we can move X, Y, theta control with a chrome mask with respect to the resist coated wafer. So there will be alignment marks on the, and we can do a double side alignment because we have double side optics, or infrared alignment is also possible. So we can control the mask, wafer distance, control the exposure intensity, and the dose of exposure also is possible. So this is one of the most used equipment in any clean room. So we have a EVG EVG 6200 infinity system for enabling photolithography for alignment and exposure. So UV photolithography, contact and proximity. So contact exposure is like we put the photo mask on top of it without any gap on top of the resist and expose it to a light source. Normally I and H line are used. And then in proximity mode, we introduce a gap which is seen here between the resist and the photo mask. So it defines if we are using proximity, we can have more gap or this gap will define the minimum feature size. The minimum feature size is given by root of d divided by L, d times L. So d being the thickness of the resist and I being the wavelength used. So if you are reducing the wavelength, you can minimize the feature size. So that's what I showed you, the technology of in the first two slides I was talking about the minimum feature size or the feature size reduced with the reduction of the wavelength that we are using in photolithography. So for extreme UV lithography, we are using 13.5 nanometer, which gives us 3 nanometer feature size. Okay, there is a lot of other optimizations also involved, but the major factor that affects the feature size is what is the wavelength you are using here. So if you are using it in proximity mode, the minimum feature size is approximately equal to root of d plus g times L, L being the wavelength. So here you can have in proximity exposure, the major advantage is that there is no risk of contamination. We can have mask in few micrometers above the substrate, so that means we are not at all in contact with the substrates or the resist. So we'll be having some small loss in resolution, but that's not a big issue if you know how to work with it. So these are the sources we use. So for 436 nanometer we use a mercury arc lamp. It's a G line. 405 is also mercury arc lamp, and we use H line for we call it as H line range. And 365 nanometer is I line. So normally we use I and H lines for our process here in Institute Lafayette. So when you are reducing the wavelength, so we can go up to deep UV, which is 250 nanometer, approximately 250 nanometer from KRF laser, and deep UV from argon fluorine excimer lasers, and then F2 laser is 157 nanometer. So extreme UV lithography is approximately close to 13.5 nanometer and below. So if you want to define feature size below this 3 nanometer, you have to use X-rays for which the wavelength is tunable. So after I finish my lecture, if the time permits, I will talk about E-beam lithography also. So we need, apart from these lithography facilities, we need wet etching. So we have wet etching chambers, which is automatically done. So the solvent chemistry based on wet processor for metal liftoff. We use DMSO at 80 bar at 80 degrees C. So it is automatically done. So we can use different chemicals all without touching the wafers or the chemicals in this system without any issues. So we can do dry etching also. That's a wet bench. This is a dry etching capabilities. We use ICP and RIE, reactive ion etching systems. Here also we can go up to 8-inch. We can etch using chlorine and fluorine chemistries. We can basically etch gallium nitride or 3 nitrides and 3 5s without any issues. Silicon and silicon nitride also can be patterned using these dry and wet etching machines. Metal contacts, we have E-beam evaporator and then vacuum evaporator, and also we have sputtering units in our disposal. We have rapid thermal annealing systems, and also we have probe stations in between to characterize all these devices. So on a whole, we have in-house facilities to realize LEDs or fabricate a LED device in Georgia Tech, Europe. So we start from epitaxy. We have 3 MOCVD systems, and then we have clean room that is equipped with all these systems, which enable us to realize a good light emitting diodes. So I'm not going to talk about the efficiency because we are not measuring it here, but we are doing good kind of research using these systems here in Georgia Tech, Europe. So these are different characterization facilities that is available with us. So we have SEM, optical profilometer, diffractometer, and then ellipsometer, UV FTIR spectrometer, Kelvin probes, and then different setups that we need, which are most essential parts for realizing fabricated devices. So then I will come back to lithography process. So here is a process flow for lithography. So first we have to design the data of the microstructure or nanostructure that we want to realize in our wafer. So first thing is to realize this data for microburr nanostructure in our device wafer. So for that we use a computer-aided design. We draw whatever the patterns we need on a wafer on a computer first using a CAD software, and then we transfer it to a photomask. Photomask, we use photomasks or we use soda lime glass. On top of it, we coat chromium and directly write with a laser beam the patterns that we have in the CAD drawing, and then we transfer this pattern or yeah. Okay, so we process our design into a photo mask. Once we have this photo mask, we take it to a lithography machine or mask aligner, and then we expose these photo mask patterns into our device. So for different patterns, we use different masks. So this is a big process, but I will show you in short what we are talking about. So in these lithography machines, so we have different sources. So INH lines is UV source, DPV is 150 to 250 nanometers. So with INH, we can go approximately 1 micrometer or less. Submicrometer is not realized with lithography. If you want to go submicrometer, you have to always use X-ray in lab scale. So with DPV and extreme UV, you can go submicrometer, but DPV is not equipped in our Institute Lafayette, so we cannot go below submicron. And then we coat, we expose our resist with this source, and then transfer the patterns into our microburr nanostructure into our substrates or to our LEDs, LED wafers, and then we realize. So here you can see how we are, by changing the source of these lithography machines, how we are reducing the pattern size and relatively when we achieved it. So in 1971, we were using 10 micrometer pattern or microstructures were 10 micrometer in size. For that, we were using INH lines. So it went down using the same process. We changed to DPV, and we were using, or the minimum feature size was 130 nanometer in 2001. So in 2014, we were close to 22 nanometer. Okay, 22 nanometer. And then when we are using extreme UV lithography, we were at 14 nanometers. And then we consequently, in 10 years of time, we have reduced the 14 nanometer to 3 nanometer. We are still saying that there is a limit for that, but we don't know whether there is a limit for that because we are hitting the quantum limits for this. But we don't know how the future will evolve. But we already have 2 nanometer process in a commercial scale, or it is in the process of development. So this is just for the photo mask design cost. So you can see that for 5 nanometer, the cost, advanced design cost, is close to $500 million. So it's 542 million for up to validation. So it can cost almost $500 million for us to design the photomask because it is a very, very tedious process. And the wafer cost with respect to the number of runs, you can see that for 7 nanometer, it is almost 1,000 or 1,000 times higher than 250 nanometer. So if we are reducing the maximum feature size or the technological node size, you can see that the cost also increases exponentially. So again, lithography process flow. So we start with substrate preparation. We coat a photoresist. Normally it's a polymer layer which can cross-link when we are exposing it to a light. And then we expose it, we put a photomask in contact or proximity mode, and then we expose it to the I or H lines, and then we transfer the patterns onto the photoresist first. And then further, we do wet or dry etching to transfer this pattern into our wafers like this. So we'll expose the photoresist to a chemical or a developer to remove the photoresist and transfer our patterns onto the wafer. So this is the entire process, but we need these many systems for that. So for our lab scale processes, the photomask will not be that expensive. But if you are talking about industrial processor, you can see that the cost can be as high as $5 million for one photomask. Even though if you have all the designs in hand, the writing process itself is very, very expensive. It can cost us up to $5 million. So talking about photoresist is a liquid mixture or polymer liquid mixture that can be spun onto a substrate, exposed and developed into patterns for further processing. So typically it consists of three components. We have resin, sensitizer, and solvent. So solvent is normally a butyl acetate, xylene. So it is kept, it is used to keep the resist in liquid form. Sensitizer is a photoactive compound or photosensitive material. Resin is a binder that provides mechanical properties like adhesion and chemical resistance to the photoresist. So normally we say that polymer is bad, but without polymer, there will be no existence of semiconductor devices because photoresist is very, very important for these processes. So there are two types of photoresists. There is positive and negative photoresist. So if you have a photomask like this, if you are using a photoresist, you can have a resist pattern like this. So the exposed area will be retained, or unexposed area will be retained for if you are using a positive resist. If you are losing the unexposed area, that means you are using a negative resist. So the photoresist will exist all over the area where you have exposed it to light or I and H lines, for example. So this is the negative photoresist and positive photoresist. So in real time, this is the cross-sectional view. So if you are using a substrate and then coat a photoresist and expose it to light, you will see that if you are using a positive photoresist, you will lose the exposed area. And if you are using a negative photoresist, you retain the exposed area. So this is the basic difference between positive and negative photoresist. So the resolution, contrast, sensitivity, and edge resistance and spectral response curve, everything relies on what kind of photoresist you are using. So normally the resist can be Kodak 809 UV for positive resist. The sensitivity, exposure, and thickness all depends on the properties of your photoresist. So normally we can use 1 micrometer thick photoresist. We can spin coat them, and all these properties depends on what kind of cross-linking you can have when you are exposing it to light. So it depends on the photoresists. We use different photoresists for different applications, of course. So photoresist process flow, the first thing we will do after we get the wafer from the epitaxy is that we clean the wafer to remove the oxide layers from top of it, and then we'll put it in a vacuum chunk and do a spin coating of photoresist on top of it. So first we'll be rotating slowly, and then we'll increase the speed to have better drying characteristics and thicknesses. So you can see that with spin speed RPM, we can reduce the thickness of the resist that is on top of the substrate. So this is the physics of the spin. So you have the equations related to these. The overall result is that post-spin thickness will be 1 divided by omega. So where omega is the spin rotational speed in RPM per thousand. So the best way is to find the spin curve with respect to the thicknesses. So, and for each polymer or each photoresist, we have different curves. And because if you see it here, each photoresist will have different properties because the polymer or monomer inside these photoresists are different. So it has different viscosity, drying characteristics, and dispense volume will be different. So each photoresist needs different spin physics to optimize them. So you can see it, SU8 with respect to the evolution of SU8 with respect to the years. So you can see that for each polymer, we need to optimize it further. So typically, we spin it for 20 seconds at a peak speed to have a respectable thickness of photoresist on top of these materials or wafers. So after we coat these photoresists on wafer, we normally do a pre-bake, which is a soft bake, which will be at a lower temperature to evaporate the solvent from the photoresist. Once we do that, we do a alignment. We take these wafer with photoresist for alignment and expose the I and H lines on top of these wafers. After this, we will be doing a post-exposure bake or hard bake, and then develop the resist so that we can define patterns on top of it. After which we'll be doing a hard bake. Hard bake is normally at a little bit higher temperature or close to the glass transition temperature of the polymer we are using in the photoresist. So for positive resist and negative resist, as I told you, depending on what kind of chemistry we are using, you will have something like these. So for normal development, we will have substrate that is exposed to air without any photoresist. This is incomplete development. You can see some photoresist on top of the substrate. If you are etching more substrate, this is under development, and if you are over developing, you can etch the wafers also, depending on what kind of you are using. So normally for gallium wafers, they are chemically very robust. So normally you will not be able to etch gallium nitride wafers using non-metal chemicals. So if you want to etch gallium nitride, you have to use potassium hydroxide HN to etch more gallium nitride, but that's not compatible with photoresist also. So post-exposure baking is often needed for negative resist, but optional for positive resist. Is always needed for chemically amplified resist. So if you have a very robust photoresist, you will be using post-exposure baking. But other than that, we don't need them. So this is just to enhance the cross-linking of the polymer. So we'll be heating up close to the glass transition temperature of the polymer, and then we'll be completely polymerizing these, or we'll form the cross-linking and polymerize the photoresist. So there is post-bake or hard bake after we transfer the pattern. So high temperature bake is used to stabilize the hardened resist. So it is just to improve the adhesion to the substrate. We are doing this so that it will be stable during further processing of these materials. So this is done a little bit higher than the glass transition temperature of the polymer. So it introduces a lot of stress in the photoresist. Sometimes it is bad. It is bad depending on the resist. If you are increasing a lot of time and temperature, it can be really difficult to remove these from the substrate. So because the adhesion will be improved if you are close to the glass transition temperature, and it will be really hard for us to dissolve them from the substrate. So it has to be again further optimized to have for each photoresist you have to know under what conditions you can realize post-bake, pre-bake, and soft bake. So once we realize these, we can remove the photoresist. So this we call it as lift off or removal of the photoresist and its residues. The residues are really painful because if we have residues in the wafers, it will be really painful for us to put metal contacts on top of it, or further processing will be really difficult. So for these photoresist removal or lift off, we use simple solvents like acetone. For positive resist, we use acetone. For negative resist, we use methyl ethyl ketone or methyl isobutyl ketone, piranha up to 150 degrees C to have these residues and the photoresist lifted off from the substrates. So we can use oxygen plasma etching also. It is a very effective cleaning tool to remove the organic polymer debris. So the residues, again, it is a little bit hard for us to remove the debris because we will be having butt joints, or you can see that we have an undercut profile here. So undercut profiles, normally it is like a straight line here. We call it as a butt joint also because it will be always curved and it retains a lot of residue. So if it retains these residue, it will be hard for us to put metal contacts and have a specific contact resistance to a lower value. So normally we avoid these by processing bi-level resist or tri-level resist, and we use a proper RIE etching tool to realize a good joint or good what we call a good aspect ratio patterns on top of this mask. So we have primarily two transfer techniques. One is direct etch and the other one is lift off. So lift off is almost never used in industry due to low yield and metal debris in lift off solution, so that fall on other parts of the wafers. So what we do here is we in direct etch, we coat the material and then we coat the photoresist on top of it, expose it, and transfer the photo pattern to the photoresist, etch the films using photoresist and mask, or photoresist as a mask, and then we remove the photoresist and realize the pattern or transfer the patterns onto the wafer or coated layer without having any risk of damage. So we can do lift off also. Here we first take the substrates, we coat the photoresist, and then we coat the material on top of it. And then when we are removing the photoresist, the pattern that is on the substrate will be retained, and which is on the photoresist will be removed. This process is suitable if you are doing a low temperature process, because normally the photoresist is a polymer. If your growth temperature or your polymer layer is normally malleable, or the glass transition temperature will be close to 400 degrees C, or depending on polymer, it never exceeds 400 degrees C. But you can find something for high temperature also up to 800 degrees C, but normally below 400 degrees C. If your growth temperature is below 400 degrees C, you can use lift off technique like this. But if you are talking about 1000 or more, you will be always using direct etch process, because here you will not leave any residues into your growth chamber. So usually anisotropic dry etch is preferred over wet etch, which is isotropic. For low resolution, we can use any one of these things. So if you don't have dry etch machines available, you can use wet etch also. So coming to an example of how we are realizing our devices on top of these. So we use van der Waals epitaxy of 3 nitrides. So we grew boron nitride, which is a have a question? Okay.
No question.
Then
You continue. I think somebody is double.
Okay. Okay. So
okay, continue,
for
Dr.
van
Suresh.
positive. Okay, thank you. So for boron nitride is a 2D material, so which we are using it for separating the substrates and the active layer. So here you are seeing that we are using boron nitride 5 nanometer layers on top of sapphire substrate, which is normally 430 micron thick, and it is a single crystalline substrate. So we are decoupling uh, the top layers, which is less than a micron from 430 micron crystalline substrates. But uh, if your 2D layer is thin enough, you can transfer the registry of your substrates through the 2D material into your top layer. So you here N aluminum gallium nitride is used as an interfacial buffer, and this one is the device buffer. N-type gallium nitride is a device buffer for injecting electrons into your quantum wells. And then we finish up with P-type gallium nitride layer, which will be used as a hole injector in this device. So you can see that we can, because we have 2D layers, we can remove the top portion of top portion that is above the boron nitride layer without any issues. So we can give flexibility to the inorganic material we are having on top of these. So that's why we call it as a flexible optoelectronic substrates here. So we can have lines from the tapes. That means we have quality of the materials, and also we can do a full front-end processing and get light out of it. So to qualify it, we have done a full front-end processing of these layers, and we are seeing light coming out from a probe station, which is a bright blue light. So this article featured in Semiconductor Today magazine in 2016. So we can also realize from these structures vertically stacked micro LED display. So for these, we have used van der Waals epitaxy for blue and green LEDs. The green LEDs were grown in Korea. Blue LEDs are from our lab, but for both these processes, we have grown boron nitride and gallium nitride on top of boron nitride from our lab. So for red LEDs, as I said before, red LEDs are normally 3-5 materials, and we have used remote epitaxy for that, and then we have exfoliated all three and then put them as shown in the figure here. We on top of SOI wafers, we have polyimide layer or filters for red, green, and then blue LEDs on top of it, and then we have laterally connected them and realized all color display using these technology. So we call this technology as vertically stacked lateral micro LEDs display. So in 2023, this technology holds the record for or the world record for the thinnest and the smallest pixel inorganic pixels we have in the world. So we can have almost 5,500 pixels per inch, which holds the record, or which was the record during 2023. This record was broken in 2024 by another process, which is sad. So coming to the process fabrication, so here you can see that we have the complete LED grown on boron nitride. So we need to do these kind of processing to realize vertical LEDs. So the previous one is vertically stacked lateral LEDs, but here we are using vertical LEDs, or we are removing the LEDs from the substrate, and we are contacting the top and bottom of the active layers for efficient electron injection and hole injection using metal plates. So you can see it here. We are using copper for liftoff, and also it serves as a P contact for the device. And we are using titanium, aluminum, gold, nickel, gold layers for end contact in a particular array geometry for this. So we are growing it. We put a P contact deposition, and then we put a photoresist. We deposit copper, and then we put it on a hot plate. Because of self-induced delamination, we are removing the active device using this thick copper plate. We are removing the active device. We flip it, and then we put end contact on top of it, and then we realize vertical light emitting diodes as shown in the figure here. So these are after self lift off, and then we are having individual devices or device arrays on top of these layers. We flip it and then we put N-type metal contact on top of it to get blue light from it. So these are the IV and emission characteristics of these devices. You can see that it is really flexible without any issues. There are no cracks, or mechanically there is no failure of devices when we are using these devices. That is realized by these processes. So again, coming to the lithography process, how we are realizing this in our selective area growth. Okay, so how we are going to do this is shown here. So first, we are using we design our process. So we have to exactly know what are the features that we want in our wafer. So for that, we have square, hexagon, and triangle shaped features or openings. So S means square, H means hexagon, and T means triangle. So what are the size of mask width and LED size that we need? We will be designing it, and how many patterns we need, we'll be designing it, and then we'll be doing a CAD drawing. So for example, we do a CAD drawing. So all these lines defines the mask, and openings are left in gray. So these are the markers we have, and the size and everything are etched on the photoresist using this CAD drawing. So once we realize this CAD drawing, computer aided design drawing, we transfer it to a photo mask or external vendor who will be doing as photo mask. This is a photo mask. So here we do what we do is we do a soda lime glass, and then we coat the soda lime glass with chromium, and then we do a laser writing on top of it, which will exactly transfer whatever we have in the CAD drawing onto the soda lime glass. So depending on what we need, we'll be doing a direct etch process to transfer whatever we have or whatever the patterns we have into the substrate. So after photoresist removal, we'll be having mesas, something like this, using the photo mask we have here. So the photo mask transfer, this is done externally, and then with our material, we are realizing this. So this is a wafer without silicon dioxide patterning. So for realizing sag using or transferable sag, we need a sapphire substrate. We pattern them first. Okay, so here you are seeing silicon dioxide without a sapphire wafer without silicon dioxide patterning. And here after multiple steps of patterning, you are seeing a processed wafer where you are seeing these are bigger size features and you have smaller size features which are buried here. So because the feature size are smaller underneath, the entire square is not visible, but part of it is visible because on top we have a larger feature size. So these are the optical microscope images showing the holes and the silicon dioxide. So holes are in blue, and gray area is silicon dioxide. So here you have circular, hexagon, these hexagon and triangular and square patterns here. So you can see it clearly in a higher magnification images. So these these hexagon, circular, square, and triangle. These are SCM images. You can see it clearly, hexagon, triangle, square, and circular images. So some of them are having anomalies, but for triangle, we are getting something like this because of the photo mask in some of the regions. But most of the areas are really defined. So this the feature size is 1.4 micron, or let's say we aimed for 1 micron, we get close to 1.4 micron. So this is after growth. You can see all the holes are filled. You can see that we have grown the LEDs on top of it without any issues. So this is a closer view of 1.4 micrometer feature. So you can see that we can really lift off the wafer because we are using boron nitride. Even though boron nitride does not have selectivity, we can lift off gallium nitride based LEDs on top of it without any issues. So this is the complete process. Since we cannot have images of it. I have done a modeling for you. So we take sapphire substrate. We'll be transferring silicon dioxide patterns, for example, hexagonal shape size on top of it by using SiO2 patterns. And then we coat boron nitride. This is a 2D material. And then we grow gallium nitride based devices on top of it. And then we isolate or passivate the sidewalls. And then we coat copper. And then we do a lift off. And then we put metal arrays on top of it to realize final devices like this. This is a close-up view of hexagonal LEDs on metal pads. So you can see the IV curves, light coming out of it, hexagonal and square patterns. So this is the entire process flow for realizing a flexible optoelectronic device on copper or whatever suitable transferable platform you have. So this is the device results. So you can see when you are changing the feature size or the opening size, you can go from 30 micron down to 1.4 micron. When you are at 30 micron opening, you are getting a 460 nanometer light. And when you are changing the feature size to, let's say, from 32 micron to 8 micron, that means 4 times lower, you can see that your wavelength emission is also changing. So here from 460 nanometer, you're going to 490 nanometer, which is neon. But normally by changing the feature size, you can go much lower also. You can go up to green, and we are trying to reach red using the same process. So this is the overall process as I showed you before. Not only that, we can transfer only 1 pixel to any suitable substrate. So here you have an array of LEDs, micro LED structures on top of it. So you can transfer only 1 LEDs to a glass or wood or anything, and you can contact them and you can get light out of it. So after transfer and before transfer, you can see that there is no change in optical and structural properties because everything is retained. There is no cracks or mechanical defects due to this transfer process. So this is how we are using photolithography, which is a very fundamental step of fabrication or semiconductor device processing. This is how we are using it to realize advanced flexible optoelectronic devices. So just to finish with a better note, I would like to introduce electron beam lithography. Why we are using electrons instead of photons is that we can overcome the optical diffraction limit. So because electron wavelength by de Broglie wavelength, de Broglie equation, which is lambda is equal to h by mv, you can have lambda of 0.07 nanometers. So you can reach much higher resolution by using electron beams. So that's why we are using electron beam lithography. So sub 20 nanometer features are feasible using this tool, but if you are in lab scale, it is possible. But in production scale, we use extreme UV lithography. But if you are using X-rays, you can go reach much lower feature size also. That is possible. So the cons are it is very expensive. It is very slow. That's why it is not industrially compatible. It is very slow. Normally the exposure takes days. Sometimes it takes weeks also to get a 15 nanometer or 20 nanometer patterns on top of it. We use this electron beam lithography. The SEM can be converted to 1, or we have a dedicated E-beam lithography where the energy can be as high as 100 kV. So high reproducibility can be obtained using dedicated electron beam lithography. We used a dedicated electron beam lithography also recently to realize patterns like these. So you can see the pattern size. So normally we use aluminum nitride seeded silicon, and then we coat a HSQ layer, and then we expose it to E-beam lithography and directly transfer our patterns on top of it. So this is the mask or the pattern that is transferred onto these silicon and aluminum nitride layers. So you can see the entire mask size or pattern size is 10 micron into 10 micron. The each hole opening, you can see it here, is less than 100 nanometer. To be precise, the opening size is 60 to 80 nanometer in size. So we take these patterned substrate and we realize growth on top of it. So you can see it clearly here. On the edges, we have a 2D material which has a lot of defects. And on the patterned area, you can see that we have hexagonal indium gallium nitride nanopyramids. You can see all the facets. It's perfectly crystalline without any visible defects for all these area. So here we can avoid relaxation induced defects by using nanosag process. So we can do it on different templates without any process difficulty. We can use the same process on different templates, and we can realize it on different templates. We can use it for different material also. Here we have used boron gallium nitride on top of these materials, and we have realized single crystalline material. Single crystalline boron gallium nitride with 100 nanometer thickness is really hard for us to realize, but by using nanosag, we were able to realize these boron gallium nitride single crystalline material without any issues. So we use these indium gallium nitride nanopyramids, and we have realized a device as shown here, and we have our solar cell device as shown here. We have current, and we also can get light emission from it. So this was published in 2019, but I just thought we should introduce electron beam lithography to you. That's why we were showing it to you. So with this, I would summarize. So we have done pioneering, or we have demonstrated pioneering epitaxial works with boron nitride and its alloys, van der Waals epitaxy, and nanosag with front-end processing capabilities. So innovative heteroepitaxial growth approaches on nitride heterostructures were used to tailor-make 3 nitrides that suit specific applications, and state-of-the-art novel device structures with record performances and functionalities were demonstrated. So further, we have grown boron nitride up to 6-inch diameter, and then we have used it for fundamental understanding of different growth technologies like quasi van der Waals epitaxy, and remote epitaxy. There is still, we have shown 3 nitrides are compatible with boron nitride, and it is scalable to large substrate. Further combining these technologies, we have realized micro LEDs and its transfer to suitable substrate have been demonstrated. With this, I will finish acknowledging all my colleagues who are with me for the last 15 years, working on different modules of the project and realizing this work. Thank you all, and I will be glad to answer your questions.
Yeah, thank you, Dr. Suresh. It's a very excellent talk. We are semiconductor device fabrication techniques. You given a marvelous talk. Now the talk is open for the discussion. Faculty members and students, welcome to the questions. Any clarification, any doubts from your mind? I think this talk is more relevant to lithographies techniques, the using UV lithography and as well as the EBM lithographies. The device micro LED also fabricated, that the semiconductor magazine is already arised. The talk is open for discussion. Welcome to the questions. Please.
Yeah.
Hello. Yes, please ask the questions.
Hello. Good evening,
yes.
sir.
Yeah. Good evening.
Thank you, sir, for such an impressive presentation. I would like to know that about transfer. About the flexible substrate. You stated that transfer is a very, better possibility. Is it impossible that we can do photolithography on that flexible substrate itself?
So transfer is possible. So even without transfer, you can do lithography on top of it. So the first demonstration we have done. So is without, so this LED with on the probe station you are seeing here, this is without
Yeah,
transfer. So we didn't
yes,
made
yes.
any transfer. So we realized complete LED on boron nitride, and then we did lithography on top of it to realize LEDs on these technology, or let's say on using van der Waals epitaxy. But we can transfer that also. For that, we need special multi-step photolithographic process. So that's what we are showing here. So we had to realize a photo mask, and we have to design experiments for that. So we take bare sapphire, and then we coat our silicon dioxide and transfer our patterns on top of it, and then we realize devices like these. Does it answer your question? So
Yeah, actually, one
transfer is,
problem is that with the flexible substrate that while putting this UV LED or UV light,
yeah,
it
yeah.
sometimes it squeezes or it deforms
Yeah,
also.
that's right. So yeah, if you are having a flexible substrate, you have to take care that your mask is getting aligned properly. So that's why we are using a tool, let's say EVG 6200 NT. It is a mask aligner tool. We are very careful on that. So you have to be really careful when you are using a flexible platform. You have to be really careful on that. So mask aligners is a very expensive tool which is
Yeah.
most used, or many number of hours has to be spent to align your mask to the wafers. So it should be done very, very carefully. If you are having instead of
Yeah,
rigid
and it
wafers,
needs
if
a
you are
lot of
having,
expertise also.
yeah, that's right, that's right. It needs many number of hours to be
Yeah.
spent in the lab to get these aligned. Yeah, it's not
Oh,
easy. So
yes.
you can see that.
And one more thing
You
on the
can see that
flexible
here.
substrate,
Yeah.
most of time this the electrodes, when we deposit the electrodes, they kind of when we fold it, there is kind of breakage also. I mean, the electrodes or the this patterning, sometimes it breaks on the flexible substrate. So how to
It's
overcome
possible.
that?
It's possible. It's possible. I think you had to use a proper wetting layer. If you are seeing cracks, or if you are seeing delaminations, it depends. Okay, you had to, for each problem you had to approach it differently.
Yeah. Okay.
Yeah.
Okay.
So if you are
Thank you.
using a bigger patterns and bigger things, if you are doing a flexible, or if you turn it or fold it, you will see there is a problem. You can introduce cracks in this. Yeah.
Yes. Yes.
Mm.
Okay. Thank you, sir.
Thank you.
I have a question. Like I have just doubt. So
Yeah.
for device making and then the photo masking, how
Yeah.
can we control the? I mean, I am asking about the clean room. Whether we can have a separate rooms like for MOCVD or during the device making and then photo masking. We have some kind of, we have to control the clean room, or we have a separate or we are
So
do
normally,
all these things in the
yeah.
same room.
So
Depositing
for front end
photo.
processing, yeah. For front end processing, I understand your question. So for front end processing, we use clean rooms. Lithography is done in ISO 5 class clean room, and e-beam lithography is done in a separate room, which is in a different class. So for example, it is ISO 7 grade clean room, or a class 100 clean room, and for lithography we have class 1000. And for epitaxy, we have just a room or a lab with filters in it. So we don't need a specialized clean room for that, but we need a gray room. We call it as a gray room. So it is not done all in the same room, because for each process we need different kind of control. For epitaxy, we have glove box, which is completely filled with nitrogen. So we don't need any kind of clean room for that, because the reactor is sealed in a glove box. So in this case, we don't need a clean room for that. But for lithography, we have a yellow room or ISO 5 class clean room, where we have filters installed to have less than 1,000 particles per cubic foot. And for lithography, we need much higher clean room, much higher grade clean room, because we are using electron beams to write on, or directly write on the wafers. So it is not done all in the same lab. So we have lithography separately, and then e-beam lithography separately, dry etching, wet etching, everything as separate cabinets or separate rooms. But we have a bay area which can be used to access each of these rooms. So our clean room is like the size of 500 meters square. So we can access all these.
The whole process will do continuously after depositing film or up to the end of the device making.
Yeah. So you can realize after epitaxy, all these process will take almost 1 week to 3 weeks, depending on the availability of the machines. So normally we will be using a clean room atmosphere to store the samples, so that we don't grow oxide layers on top of it. And then we'll be transferring it from one bay to another bay, like in few minutes. So like these, we don't contaminate our samples. So it's a 3-week long process. Front end processing is very long.
And also it that packaging also there, like
packaging. We don't have packaging facilities, but for small scale devices, we can use some standard packages.
Lab scale. Okay.
Yeah. Lab scale packaging is available.
Yeah. Okay. Nice to hear that. Okay. Thank you very much for my question. Thank you.
Thank you.
Any other questions, please, faculty members and students? I think this is very, very important talk in the semiconductor physics and technology. Nowadays, we have the India semiconductor mission. This mission also is doing same thing. Any questions? I think Professor Saruna is available in the talk. Sarun sir? Okay. Any other questions? Dr. Suresh, I have one clarification from your talk. You are trying to make the micro LEDs.
Yeah.
3 different layers you are filling and attaching in the silicon SiO2 substrates.
Yeah.
What is each layer thickness you are maintaining? And while filling, what will happen? The interface defect level things.
So we are bonding these.
How you are matching the interface layer? That is my important.
So we have
the resistance also will be changes.
That's right. So it's a very important technology. So we are bonding the wafers or active layers on top of SOIs silicon oxide layer. So we are using polyimide layers, which acts as bonding layer, and also it filters out the light. So if we have green light, we need only green light. So it's in an active matrix configuration. So you might have heard word AMOLED. AMOLED is active matrix organic light emitting diode. Active matrix means you can individually address the pixels you have in a device, in a display. You can individually address them. If you want one pixel to be turned on, you can turn them on by active matrix configuration. So you have to use this active matrix configuration. So to separate these devices, you are using a polyimide layer. Polyimide layer is an adhesive layer, and it also acts as a filter. It also acts as an optical filter. So you can have pure green, pure blue, pure red, and also combinations of all these lights.
Okay.
So the use of polyimide is a very, very important technology.
Important things.
Yeah.
Yeah. Thank you. Thank you very much. More informative. The towards semiconductor technology